Alright, so here we go. This is going to be, this is still the Unit 4 in dual credit chemistry. We're talking about thermochemistry. It's technically, I've done it in a different unit before, so it's actually, the notes are titled 13.3, but it's still technically Unit 4. So today, basically what we've been doing this unit is we've been talking about enthalpy, entropy, and we've actually started kind of talking about Gibbs free energy. So what we're going to do today is we're going to kind of put it all together and we're going to incorporate something called equilibrium. So first of all, if we take the Gibbs free energy equation, which we talked about in the last day of notes, we can use it algebraically to solve for any of the unknowns. So we can solve for enthalpy, or we can solve for temperature, or we can solve for entropy. And again, if you notice, all of the little circles, these are standing for standard temperature and pressure, which if you guys remember is 25 degrees Celsius, 1 atmosphere, and under 1 mole. But we're actually going to start with a new, it's not really a new, it's kind of like a rearranged if you kind of substitute a few things in, new equation for free energy. And again, it's solving for delta G. This is what we use if we are not under standard temperature, or if we're not under standard conditions. So if you notice, the little 0 is missing after the G. So if we do not have free energy under standard conditions, we have to use a separate equation in order to solve for Gibbs free energy. So, and you see a few things in there that you've seen before, maybe you don't remember. Again, our free energy is going to be equal to our free energy under standard conditions plus our rate, which if you guys remember, rate, we learned it in the gas laws and we've been using a little bit so far this chapter, but rate is going to be equal to 8.134, and this unit for this is joules per Kelvin mole. So if you don't already have that memorized, I would start memorizing it. Honestly, by the time you use it a few times, it'll be pretty easy. And then T is standing for temperature, and again, our temperature has to be in kelvins. And then we see Ln, which for those of you who have slept since math class, that is standing for your natural log, and Q is your reaction quotient, which we haven't actually done our reaction quotients yet, but it'll be really, really easy. Honestly, all you have to do to find Q is you are going to take your molar concentration, and remember we represent concentration with brackets. We take the molar concentration of our products, and we divide it by our molar concentration of our reactants. And so Q, we haven't physically done it yet, but it's really not that hard of a calculation. And again, molarities will be given to you, so then you just divide the two. Okay, so this leads us to something called K. K is kind of like a constant, and K with a little subscript of EQ is talking about the equilibrium constant. So when this reaction is at equilibrium, it is going to have this reaction constant. And sometimes you'll have to be solving for them, sometimes not. And just to kind of help you guys, because rearranging equations with logarithms can be kind of difficult, so I just went ahead and rearranged it for you. Sorry, I guess I got one step ahead of you. Okay, to rearrange the equation with a logarithm in it, I'm just going to rearrange it for you. So if we rearrange this equation to solve for, I got ahead of you guys again. Okay, I guess I need to click next in my slide. But at standard conditions, Q is going to equal 1. Okay, if our Gibbs free energy under standard conditions equals negative RT natural log of K equilibrium. So this is what I was trying to get to at a minute ago, was this equation right here. Sometimes rearranging equations to solve for something in a natural log is a little bit difficult, so I'm just going to go ahead and rearrange it for you, and there's actually a spot on your paper to write it for you. So if you're ever solving for this variable, our equilibrium constant is going to be equal to E, which is what you do for the natural logarithm, and I'll help you guys put this in your calculator if you need help. And its exponent is going to be negative Gibbs free energy under standard conditions divided by your rate times your temperature. So we just rearranged it again, and rearranging is difficult, so I just went ahead and did it for you. Okay, so continuing, if our Gibbs free energy under standard conditions is negative, then our equilibrium constant is going to have to be bigger than 1. If our Gibbs free energy is 0, then our equilibrium constant has to be 1. And if our Gibbs free energy under standard conditions is positive, then our equilibrium constant has to be smaller than 1. So if we go back and if we look at our quotient, which is up here again in the original equation, if we go back and look to this, this is where we get all of this information. So again, quotient is the concentration of your products divided by the concentration of your reactants. So basically we're looking at a division. So we have our products and we have our reactants. So if we're looking at negative, if this is bigger than 1, if this is bigger than 1, it means that our products is going to be bigger than our reactants. So if that number is bigger than 1, then it is going to give us a negative answer all around. Okay, if we look at this one, if our product is smaller and our reactants are bigger, making our denominator bigger, then our equilibrium constant is going to be smaller than 1, which is going to give us a positive answer. And then last but not least, the one in the middle, why is it equal to 0? Well, just go ahead and try it. Put the log of 1 in your calculator. Log of 1 is equal to 0. So if log of your 1 is 0, then it's going to make everything else 0 out, and therefore it's going to give us an answer of 0. So that's just a little bit of how that equation works out. All right, there's that equation again. If you haven't had a chance to write it down, there it is again for you to write it down. All right, so we've been calculating enthalpy a lot this unit. So there are 4 different ways that we have learned to calculate enthalpy. The first one, and honestly I think the easiest for you guys, is just plug it into the equation. Q equals mc delta T. Remember, C stands for the specific heat of a metal. Mass usually needs to be in kilograms. Just make sure that whatever your specific heat is, that your mass will cancel it out. The second thing we learned how to do was using Hess's law, and this is where we just add the reactants. So if it went in the forward reaction or if it went in the reverse reaction, we could figure out what the enthalpy change needed to be by adding up our reactants. And then what we've been doing, I think it was on Tuesday this week, we can take the sum of our products minus the sum of our reactants. And again, this was Hess's law, 2 different parts of Hess's law. And then we actually haven't done this way yet. We're going to be doing it here in a little bit. But we can also do the bond energies, so we can take the amount of energy that was required to break the bonds and subtracted by the amount of energy required to form the bonds. But again, we haven't done it that way yet. So now let's talk about Gibbs free energy. There's 3 ways that we can calculate Gibbs free energy. The first way is the calculation that I taught you guys to do in the previous day of notes. To find Gibbs free energy under standard temperature, or not standard, standard conditions, you take your enthalpy minus your temperature times your entropy. And for some reason, this one's a little out of order. I meant this to be number 3. And for some reason, my computer messed this up again. So this is a weird symbol. We're going to ignore that. That actually is E0, which is talking about electrochemical cells, which we're actually not going to talk about until the next unit when we're doing half cells and reactions and electricity and all of that fun stuff. So we'll just ignore that for now. But then the one I just told you about was to solve for negative RT, the natural log of your equilibrium constant. So there are lots of different ways we can get to these, and every problem you might have to do a little bit of a different way to get to the answer. But as long as you get to the answer, it really doesn't matter how you get there. So let's do an example. All right, so this is wanting us to calculate the enthalpy, the entropy, and the Gibbs free energy for the following reaction at 298 K. It is what I need you to use your appendix in your book to find the individual values. And the other day I told you that this was appendix B in our black textbooks. So basically what you need to do is you need to go ahead and look up the values, and I'll go ahead and write them down for you. So for enthalpy, it is going to be negative 296.9. This is elemental, so it's going to be 0. And then our enthalpy for our sulfur trioxide is going to be negative 395.2. Okay, we need to do the same thing for our entropy. 240 208.5, 205, and 256.2. Now in our book, it lists our enthalpy values in kilojoules per mole, and it lists our entropy values in joules per Kelvin per mole. So honestly, you should just get in the habit of converting everything to joules, and that way we won't be having to worry about units not matching up. So when I put these in my calculations here in just a minute, I'll probably go ahead and convert them to joules, so on and so forth. So it's wanting us to do all three. So let's just start with enthalpy. I wrote that one down first, so let's find enthalpy. To find enthalpy of our reaction, we're going to take the summation of our products minus the summation of our reactants. So we have a coefficient of 2 in front of our product, so we're going to do 2 times negative 395.2. And I haven't converted it to joules just yet, but I will at the end, less zeros to keep track of. Going to subtract that by the summation of my products, which is going to be, again, 2 times negative 296.9. Now, since oxygen is 0, we can just kind of omit it from the equation for right now. And if you put this in your calculator, you should get an answer of negative 196.6 kilojoules per mole, or 196,600 joules per mole. Okay, so now let's do the same thing for entropy. So to find our entropy of our reaction, we're going to do the summation of our products minus the summation of our reactants. So again, we're going to be doing 2 times 256.2, and we are going to subtract that by 2 times 248.5 plus 205. And we're going to put all that in our calculator. When I put all that in my calculator, I get negative 189.6 joules per Kelvin mole. But we are still not quite done. We have to find our entropy now. So I ran out of room, so I'm going to have to erase all this, but I'm going to need this piece of data here, or not that, this piece of data because I need it in joules, and this piece of data, I'm going to need that in just a second. So that's where I'm going to get these numbers in the next step. So to find my delta G of my reaction, I need to take my enthalpy minus my temperature times my entropy. So my enthalpy I found to be negative 196,600 joules. I'm going to subtract that by my temperature, which I was told was 298, and I'm going to take that times my entropy, which I found to be negative 189.6. Everything's in joules, everything's going to cancel out, so then I just have to put it in my calculator, and it gives me an answer of negative 140,000 joules, and I rounded. I had a lot more numbers than that in my, but I just decided the temperature is in 3. They only give us the significant figures of 3 in our temperature, so I can only keep 3 here. So my answer is going to be negative 140 kilojoules. All right, so let's look at another example. This example is a little bit more complicated, but doable nonetheless. So this one says calculate the delta H, the delta S, and the delta G for the following reactions at 298 Kelvin. Use the appendix in your book to solve for the individual values. So just apparently my slides are a little bit out of order, and that's fine. Let me find the example I wanted to do. This is the example I wanted to do. Okay, consider the ammonia synthesis reaction into gas plus 3 hydrogen gives you 2 NH3 gas. So it tells us that our delta G is going to equal negative 33.3 kilojoules per mole of N2 consumed at 25 degrees Celsius. Calculate the value of the equilibrium constant. So this time around we are solving for K. So we need to use K equilibrium is equal to E to the negative delta G divided by RT. Alright, so we just have to, basically, we're going to have to learn how to put this in the calculator, keeping track of all of our negatives and our units and keeping everything in the same spot, so on and so forth. So it's going to be E to the negative. My G is given to me up here, but it's in kilojoules, and we have to be in joules because our rate is in joules, so I'm just going to move the decimal over 3 times. Joules. Okay, and then I'm going to divide that by my rate, which is 8.134, times my temperature, which is 298. So honestly, in this problem, all you have to do is plug the numbers into the calculator and write down your answer. Now, I'm hoping I did this correctly. I really hope that I did it correctly, but my answer is going to be 92542. Now, since my number that was given to me in the problem only had 3 significant figures, I have to round it with 3 significant figures, so my answer is going to be 92500. And if you notice, no units. Why are there no units? Because if we would have put all of our units in our work, we would have seen that all of our units would have canceled out, which makes sense because this is a equilibrium constant. Constants don't always have units. Alright, so let's move on to the next one. Example number 7 on notes today. Let's see if Alright, this one is not hard. It's just we've never done one like this before, so it's going to be a little bit more difficult. Plus, I forgot to actually type something in here. So it says calculate the value of delta G under standard conditions for the following reactions at 389 Kelvin, where the concentration of NH3 is 2, if H2 is 1.25, and if N2 is 3.01, and it gives you a balanced equation. So the one piece of information that I forgot to tell you was that it's asking us to calculate what is the value of delta G, not delta G under standard conditions, so ignore that little circle right there. The question's asking you to calculate what the value is of our free energy when we are not under standard conditions. And then the piece of information I forgot to give you is our delta G under standard conditions is going to be equal to negative 16.66 kilojoules. So now we need to solve for delta G. So we're going to be using this equation that I told you earlier. To solve for delta G when we're not under standard conditions, you take the free energy of standard conditions, you subtract it by your rate times your temperature and your natural log of your quotient, which is again the concentration of the products divided by the concentration of the reactants. So again, all we have to do is plug this into the equation and then put it in our calculator. So our delta G under standard conditions is negative 16660 joules. I had to convert it to joules to get my rate to cancel out. Okay. Next, I need to subtract it by my rate, which is 8.134. My temperature is 389 Kelvin. And then I need to times it by my Q, and I ran out of room, so I'm just going to go ahead and do that down here. But my Q, we're going to take the concentration of our product. Our product is NH3. NH3 up here told us that it was 2 molar, so I'm going to take 2 molar. Divided by the concentration of our reactants. Well, we have 2 reactants, so all you have to do is multiply them together. So I'm going to do 3.01 times 1.25. However, it's not just that simple because we have a balanced equation, which means we have these coefficients. So we have to have some way of putting these coefficients in on our quotient, which is really easy. This coefficient, the 2 right here, it's going to be an exponent now, right there. And the coefficient 3 on hydrogen is going to become an exponent on our concentration for hydrogen. So now all we have to do is, again, plug this into the calculator. I cannot stress enough that you have to make sure that you are following your order of operations and you're putting everything in correctly, or you're going to accidentally make a silly mistake like I just did. I forgot to write my natural log. I probably would have forgot to put that in the calculator if I wouldn't have just realized I forgot to do that. So once you put all of this fun stuff in your calculator, you should get 15441 joules per mole. But we need to follow significant figures. In our problem, one of our molarities only has 2, so that means my answer can only have 2. So it's going to be 15,000 joules per mole. All right, so hopefully we're not 100% lost. Hopefully we're doing pretty good. Monday, when you guys get back, is going to be review day, and we're going to do practicing of all of the different types of equations that we learned. Please come prepared with questions.